next speaker is Dmitry who is going to talk about Smarr formulas and rod structure. Please go ahead.
Okay, thank you very much. I'm very glad to be able to, to speak at this nostalgic meeting. 34 years after historical quantum gravity, where this picture was taken. Yes, it was May 25th, 1987. And to give you an idea of what was Moscow at the time, it's another picture. It was 3 days after. It was a border guard day. If you like any comment, or those who don't understand what is this, I can do it later. Now, the topic is about Smarr, and this is a historical paper by Smarr of 1972, which was preceded by two even more historical. One is Christodoulou. Christodoulou was the first who showed the usefulness of the concept of black hole area, horizon area. And he considers irreducible mass of black hole. He cannot be diminished in any processes. And he called it reducible mass. And then Hawking soon after showed that the area of black holes can never decrease when he derived the constraint on the gravitational radiation from colliding black holes. And now the paper by Smarr, it was 72. Smarr, what he did, he took the Kerr-Newman metric, and this is the area of the horizon of Kerr-Newman metric. He extracted from that the mass in terms of area and other parameters. The angular momentum here is denoted by L. Omega is the angular velocity of the horizon, phi is potential of the horizon, q is charge. Now he said that T is effective surface tension. So that time it was considered as mechanical term, TdA is mechanical term, and just if you stretch the horizon, so you increase its mass by tension term. And then the modern derivation was given just 1 year later by Carter in his famous book Black Holes in Les Ouches school. And he started by Comor integrals. Comor integrals are just these guys. The K is a Killing vector expressing stationarity. It is dt actually, and M is axial d phi. So these derivatives are antisymmetric, forming two forms, dk, dm, and one can operate with them exactly the same way as with Maxwell form and electrodynamics. If you integrate over the two surface at infinity, you obtain the total mass. And if you integrate another Killing vector azimuthal, you will get the angular momentum. And just using a Stargardsky Gauss, you can transform this integral for mass at the infinite surface through the surface integrals where sigma n is surfaces surrounding all the object. It is black hole horizon. If you several black hole horizons, if you have defects, and this will be our situation now, like cosmic strings between the black holes, or struts, or Misner strings. You will get the sum of those surface integral over the sources, particular surface of the solution. And M is the total mass of the whole configuration, which also include the bulk contribution by Strogatsky-Gauss. And this bulk contribution using the Killing equation can be expressed through the energy moment of the Ricci tensor, and then by the energy momentum tensor. So it will be bulk contribution of fields. Carter applied this to Einstein-Maxwell, and apparently it can be generalized to other systems, including scalar field without potentials. I will say about that a bit later. The same you can do for angular momentum, taking the azimuthal Killing vector here. And to derive the Smarr relation, you consider the linear combination of two Killings, just well known from black hole physics. It's k plus omega h, which is the angular velocity of the horizon, m. So on the horizon, it is just vector psi, which becomes null. That is, the event horizon is the Killing horizon of psi for rotating black hole. For Schwarzschild black hole, it is just the Killing horizon of k. And that way you derive the term with integration of psi, which give you area of the horizon. And you exactly in differential form, you obtain the Smarr formula in that way. Now k is already kappa. Kappa is already different. Kappa is a square, K square of surface gravity. Now, an important remark now is that if you take just the space-like Killing vector m and consider its norm, you can see that on the symmetry axis, theta equal to 0, it also becomes null. So the polar axis is actually a Killing horizon for, yes? Sorry, the Killing horizon for the azimuthal Killing vector. And the difference with the black hole horizon is that outside the axis, it is space-like. On the axis, it is null, but there is no inside region. So one of the main applications of what will be happening is just the spacetimes with magnetic mass, which produce you defects on the polar axis known as Misner strings. So such spacetimes usually often rejected as unphysical because of they have this singularity, and to eliminate singularity, make it unobservable, you need to identify the time. But when you identify time, it will be already just a toy model, but not a realistic thing. So long ago, Bonner suggested not to do it, but just to consider the polar axis like a true singularity. It is singularity which usually called weak, because the square of the Riemann tensor doesn't diverge there. It has a divergence only of Ricci tensor of delta function type. So it is a distributional divergence. It's a question how to calculate it, but it can be done. Now, if you don't identify, you will give singular spacetime, which apparently will violate many of black hole theorems, uniqueness theorem, for instance. But you can still work it and with it. And we have shown in this paper that the problems like closed time like curves which occurs near the polar axis in the near region around the polar axis, they don't contain the geodesics, so it doesn't lead to observable effects. So observable effects with those problems of Taub knot actually were not discussed much in the literature. An interesting example is that if you take Kerr-Newman knot and you take a super extremal case, which without knot, it would be a naked singularity, but with knot, it is a regular solution. And it has a topology of wormholes. And this is a paper where it was investigated. Also, there are no, we did not find any observable pathological feature associated with those problems of knots. So there are reasons to work more on that. Now about rods. So let us pass to Weyl coordinates. And this is a parameterization of Weyl. This rho and z is actually cylindrical like coordinates phi and t. This representation of the interval is very useful because it makes for potential for the function u an equation which is flat spatial plus equation in vacuum. And then after you integrate this equation, you can just consider two partial differential equations which are consistent, and you obtain the solution. Now the Schwarzschild in those Weyl coordinate reads like looks like a Newtonian potential of a finite rod, literally a rod, located on the segment of the axis z between minus m plus m. Now, so in those papers, we consider the situation where we actually repeating the reasoning by Carter, but allowing for line singularity on the axis. It is useful for multi-center solution, for instance, aligned multi-center solutions like with struts between the centers, like binary black holes. There's a lot of them, and also for knots, and also for magnetically charged solution with Dirac strings. So the useful construction to treat these things in universal way is so-called rod structure, which allows you finally to express individual masses of multi-component solutions containing strings, struts, and so on, and black holes. Now, more about rods. There are actually several classes of metrics, not only four-dimensional. In four-dimensional, it's Papa-Petru interval, the stationary axisymmetric, which is parameterized by u and also function a and nu. So these are equations for those functions. Another case is the metric in d dimensions with d minus 2 commuting orthogonal Killing vectors. It's something like that. This is a typical construction which occurred in 5 dimensions, for instance, when analyzing the solutions known as black rings. You can introduce 3-dimensional Euclidean space, and then the function g, which is first Okay. G is d-2 dimensional metric, conformal metric for the case of d-2 killing vector. So the components of this matrix G along the killing directions of the whole space-time metric. Actually, one can derive several general feature for that matrix. For r greater than 0, it is a nonlinear equation of that type for static solutions. But as r goes to 0, and the product of eigenvalues of those G, which is r squared, is going to 0. So if you have two degenerate eigenvalues, you will get, one can show that you will get a strong curvature singularity, and we don't like it. So to avoid that, we require that there is only one solution for 0 eigenvector of this matrix, or a dimension of kernel of G. The first argument is R here. It is the axis, and then another Z is along the axis. Now, the requirement is that the dimension of a kernel, so the solution is unique, except for several isolated points on the axis, which is called turning points. We can enumerate them, and in those points, the solution is really singular. But actually, you can do the following. So you first solve this equation for 0 eigenvectors of the matrix G, and you find that there is a unique eigenvector for each interval between turning points, and you have to match them, of course, in the turning points. So the eigenvectors will be called directions of the road. So it is direction, which is nothing that some vector in 4 dimensions, 2-dimensional matrix along T and phi, with components T and phi. And the direction is some direction in the space T phi. The rod structure, it is the following. It is a structure consisting of all turning points and null vectors, which are uniquely defined in each rod. Now you can show that if you parameterize the diagonal matrix element like that, on the axis, you will get generically, you will get a delta function singularity. And so which defects are can be described that way. First, Misner strings are there, struts between which supporting different sources in aligned multi-black hole solutions also there. It is believed that the structure of rods, so their turning points and directions, is in one-to-one corresponding with the solutions, which are we are looking for asymptotically flat or asymptotically locally flat solutions with defects. This conjecture is proved. Rigorously proved only in diagonal case, or only in the static case, but in the non-diagonal, it is a conjecture. The rod structure of Kerr is the following. There is a horizon rod between points minus alpha alpha. It is just the position of the horizon with Weyl coordinate r equal to 0 on the axis. And the direction is x1 is time, so dt plus omega d phi. Omega is angular velocity of the horizon. Then, while other roads are infinite, it is minus, it is the polar axis, and this is the south pole, and this is the north pole. And here is just d phi. So this structure rather simple. We then can calculate the norm of the eigenvectors. And in principle, they can be time-like, space-like, and null. Typically, in solutions we are considering it as time-like or space-like. And all the horizon are finite time-like rods. So in kinemetrics, this rod interior is just the horizon. Now, an important claim is that vectors, which are eigenvectors of the Gram matrix, are constant along each chosen rod. So this eigenvector is, and this basically means that there are two quantities which are constant on the horizon. We will see later. It is the surface gravity and the angular velocity of the horizon. And this is another way to state these two important claims of the whole physics. Once again, we have, let me denote it like L now, and consider D equal 4. So this L will be two-dimensional vectors in the space of T and phi coordinates, and basically can be expanded in terms of K and M. Near the road, the norm scales as rho square, where rho is radial Weyl coordinates. And this also follows from Einstein equations. This is for vacuum case first. Now, finite time-like rods correspond to black hole horizon, and the associated surface gravity, which is usually defined. This vector is defined only on the axis, but of course it is can be prolongated outside the axis, and it defines the killing vector of the space-time. And so now, in this sense, there are covariant derivatives. This usual derivation of surface gravity, and in terms of this boundary values of those vectors, it is just that quantity. So we see that the norm of LH, it can be chosen in such a way that KH may be given any prescribed value, for instance, 1. So such normalized rod direction will be parameterized by two quantities, by surface gravity and angular velocity of the horizon. And the theorem that the rod direction is a constant vector along the road, it is just now equivalent to constancy of this surface gravity and the angular velocity of the horizon. But the same is true for space-like rods. What are space-like rods? Space-like rod is just the Misner strings, for instance, or struts in multi-black hole solution. For them, the eigenvalues of the rod are space-like vectors. But they can be parameterized by the same way, like those vectors for the horizon, introducing the same quantity, which can be called space-like surface gravity, and also angular velocity. So the meaning is the same. It is true physical angular velocity of the defect. And the meaning of the surface gravity is less clear, because we deal with something which was outside the defect. It was space-like, and it became null. So it is the killing horizon, still killing horizon on the defect. The formula will be the same. So basically, such vectors will fix you some direction, along which you have to identify, make an identification to avoid conical singularity. And the correct identification which does it is this one. So the period of the coordinate eta, for which this vector will be d eta, just the Killing coordinates, it will be 2 pi by the limiting value of that thing. If you do not this, you will get conical singularity. But actually for struts, you don't need to do this. But you consider this as physical defect. In presence of such things, you can rederive the Smarr formula, starting again with the Killing comma with the comma at infinity first for time like k, then transforming it to, and we consider here, we consider Einstein-Maxwell system, and transforming it by Ostrogradsky-Gauss to sum of surfaces of the surfaces over surrounding the defects now, and the bulk contribution here. No, here bulk already transformed into the bulk contribution because of Maxwell equations. One can show that one deals with some full divergence, and you can transform the bulk here again to the surface. So all the whole mass will be expressed through this thing, and so the sum like that, the sum of mn. Similarly, for angular momentum, taking the Killing vector m here. Now, essentially useful here is the Tomimatsu formalism. Tomimatsu was able to express these two-dimensional quantities through one-dimensional over the axis. And very useful are Ernst potential. This is here Einstein-Maxwell system, so this is the standard Ernst potential for that, related to electric component of the field, and dualized U, which is another component of vector potential, which dualized to magnetic potential, and twist potential, which is dualization of the rotation function omega in the interval. Then you using that, you can transform already onto the axis integral, one-dimensional, between the turning points. So the contribution of each rod will be the integral between Zn and Zn plus 1 turning point of that rod from such quantities. And the integral is easy evaluated, so it just gives you this algebraic relation. This algebraic relation is nothing but analog of the Smarr relation, but only for one component of the full solution, which may consist of many black holes. So if you have only one, so it is just it reproduces you, of course, reproduce you, for instance, Reisner-Nossen, because there is a charge here. But now it is more than that, because it is the individual contribution of each component. You can do this in the similar way. Excuse me. With rotational Killing vector, and you obtain the angular momentum of one chosen defect in terms of integral over the axis only, in terms of the same quantities, Ernst potentials. And what is interesting, the first term in the angular momentum will be just the length of the rod. And omega n is nothing but the inverse on the defect, the inverse angular velocity of this defect. So one can recognize here something related to contribution of angular momentum multiplied to the mass. If we invert this formula, we obtain angular momentum of the rod in terms of mass and the quantity omega g. But what is interesting is that this quantity is nothing but the distance, is nothing but the distance on the axis. And the distance on the axis can be expressed also as the area of the horizon, because it is seemingly as a one-dimensional effect, but the integral over dz, it is nothing but the integral on the surface which is surrounding, cylindrical surface around it, because it is singular, and this quantity when integrated gives you something like that. So the correct identification of this is just that the distance along the axis is k kappa, which is the surface gravity of the horizon, by the area of the horizon. And this simplicity was due to using Tomimatsu Sato, and we notice that there is no much difference between the horizon of a black hole or space-like defect, because the same formula actually holds for space-like defects too.
Dmitry, you are about beyond 30 minutes. Could
Okay.
you finish within a couple of minutes or 5 minutes, let's say?
Okay. Now, inverting this, we get the Smarr relation for individual rod like that. And the quantity, which is the length of the rod here, it is the same as surface gravity by the area of the horizon divided by 2 pi. It is just the exact equivalence. Now, the whole mass, asymptotic mass, will be can be separated on the contribution of horizons if you have several black hole components, and the contribution of defects on the axis. But it looks the same way if you treat now how you treat area. So here in the defect case, of course the simplest way is to treat it the same as entropy of the black hole horizon. Maybe it's not so much clear. Here I explained that the Dirac string in electromagnetic solutions with magnetic monopoles, which is usually considered as an artifact of vector potential, but when gravity is taken into account, it is really heavy and it has the mass, and it explains you the difference. So this is the case of Kern-Newman metric with electric and magnetic mass. Now the horizon mass Smarr formula does not contain contribution of magnetic mass because it is only Dirac string which contains. So asymptotical contains, and you can put it in the form, usual form as a product of potential on the charge, but actual meaning, it is the mass of the Dirac string. You can calculate it, the defect mass using the formalism which was previously. Now, exact computations for Kerr gives you the following. This is the usual formula for surface gravity angular velocity of the horizon, but here for defect. And the defects are just Misner strings here. So you can treat this kappa as a temperature of the defect, but it would be very strange because there are no other ingredients for that in this case. The only one is that it is a killing horizon, and the killing vector actually for the Misner string, killing vector become null on its surface. So the surface gravity can be obtained that formally in the same way as black hole gravity, but actually we don't have much reasoning to treat it as true entropy. So another interpretation of mass will be that way. So it is just the mechanical terms of two Misner strings. Each of them rotate with omega plus and omega minus, and this is the angular momenta. And this interpretation favors, of course, the symmetric gauge for the Misner string, symmetric under replacement north-south, because both these quantities for infinite Misner string, they diverge, but the sum in symmetric gauge, they cancel. And finally, you can establish that everything is okay with this solution up to interpretation of those things. You can both interpret them as surface gravity and the area as an entropy, but the surface gravity not with the temperature. So it will be somewhat unusual. Anyway, but most of interpretations met in the literature, just like this, it is the entropy of Misner strings, starting by Hawk and Hunter, Mann, more recently Kubiznak, and many other people. Another interpretation is a mechanical term, which is finally due to the fact that if you stretch the string, you will do mechanical work. Now you can generalize this to Einstein-Maxwell dilaton. And I think that for generic supergravity actions which don't have potentials but have the structure like that, Maxwell terms multiplied by dilatonic exponent, actually we'll get the same. And in the final formula, even dilaton disappears completely because those observable in the redefinition of charges, with the redefinition of charges, of course. And this is an example of two-component solutions, which we consider in this paper. There are two black holes inside the unique ergo region. This black hole have mass, electric charge, also magnetic charges, opposite electric charges equal, magnetic opposite, and opposite not charges. Because of that, it doesn't have Dirac string or Misner string outside this configuration. Outside the configuration is completely empty. There are only long distance fields, but no defects on the axis. And asymptotically, it is Kerr. Asymptotically, it is Kerr, and it could seem to violate the uniqueness for Kerr. It is in 4 dimensions, but of course, the price is that the solution has naked singularity on the axis, and this axis, but it is very mild naked singularity. It is nothing but the distributional singularity of cosmic string nature, which is at the same time Dirac string and Misner string. And using this formula, you can establish that the full masses consist of masses of black holes and masses of mass of the string and the same for momentum. So it perfectly well works. So struts, my conclusion is the following. Struts and Misner strings do contribute to asymptotic mass Smarr formulas. And they contain the surface term. This surface term is just correspond to space-like the products of space-like surface gravity by the area surrounding the string. And the big question is if there are reasons to interpret this as entropies, or just in mechanical terms, because if you deform this configuration, you make also mechanical work. So it is still to be discussed. But the entropic interpretation is favored by analogy with Killing horizon also, because there is a two-dimensional diffeomorphism algebra. If you consider Killing horizon as a boundary, you will get the two-dimensional extension of the constraint algebra with central charges. And those central charges were identified, which are given by Cardi formula, identified with the entropy. But and this argument works here, in spite of the fact that inside this Killing horizon there is nothing. There is no internal region. Now the component horizon mass Smarr formula do not contain contribution of magnetic charge or not charges because they are global. And those contributions are contained in the careful evaluation of the parameters of Misner string and the Dirac strings. So Dirac strings gravitational are heavy. They cannot be just considered as artifact because we can make it unabsorbable by quantum particles in flat space, but in gravity you cannot. They are heavy. And also from our analysis, it follows that only symmetric north-south configuration for both Dirac string and Misner strings is consistent and doesn't diverge. And finally, the multi-component solutions can be just treated at so mass and the angular momentum of multi-component solution is just additive quantities. They are added like numbers. There is nothing nonlinear in the superposition, while the field, gravitational field, of course, itself is effectively nonlinear superposition. So now I finished. And this picture is from new museum in St. Petersburg, Museum of Modern Art, which is called Gerard. Thank you very much.
Thank you, Dmitry. So unfortunately, we have time for only one short question. Yes, Sergey?
Hello. So I would like to ask how this derivation actually affects the uniqueness, and in the sense that, I mean, we can introduce some kind of rod structure even if we have a cosmological concept. I mean, of course, the theory would not be integrable in this case, but still, can we say something? Can we apply some kind of this derivation? Because, well, the Stoke and because the Stoke Yazagiev and Hollands, their construction of the rod structure essentially is applicable to the cosmological, the case of the cosmological constant as well. So can we actually say something about the uniqueness in this case?
Let me try to come back to.
Please a very short answer because time is.
Okay, I just answer that you cannot directly incorporate here cosmological constant. It's change this structure. What we need is admissible only Maxwell terms, maybe multiplied by scalar exponents and free scalar field, but any potential type, including cosmological constant also, is not consistent with this treatment. I'm afraid that I have a problem to get back to to sharing the screen.
I'm sorry, but we have to move on to the next talk.
Okay.
Thank you again.